In this video, we're going to talk about graphing a derivative. Our outcomes are to graph a derivative function from the graph of a given function, state the connection between derivatives and continuity, and describe three conditions for when a function does not have a derivative. So our derivatives of a function, think about lines. A line has a positive slope if it's increasing from left to right, has a negative slope if it's decreasing from left to right, and a horizontal line has a slope of 0. A vertical line has an undefined slope. I mean, you have rise but no run. So basically you have change in y but no change in x. So change in x is 0. So let's take a look at where we're going to go with this. Here we have f of x is the square root of x, and we saw in the last lesson the derivative is 1 over 2 times the square root of x, and that has a curve like this. And remember, what the derivative is showing is the slope at any given point. So the slope of this blue line, f of x equals the square root of x, has a slope that's steep here in the beginning, and it gets less and less and less steep as you go along, so that the slope is getting smaller. Now look at this one. This means it's a really high number here. The slope's a high number, and it's getting smaller, but it's staying positive the whole time. So it's going to stay positive, but it gets smaller. Means this curve is starting to level out. And that's a key thing to think about the slope. Don't think about the slope as giving value to this function. It's giving value to the slope of this original function. So that's our derivative. We also worked a problem f of x equals x squared minus 2x, and the derivative was 2x minus 2. This is the equation of a line. So if we look at the graph of this, here's our original function. It's a nice, pretty parabola. And the derivative is this orange is a line. And so what I want to point out here is at 0, when y is 0, and it changes from being a negative slope to a positive slope, that's when we're reaching the bottom of this curve to where it has a negative slope. It's less and less negative, less and less negative. Then it gets to here, it bottoms out, and then it starts becoming positive. And we see that change occur here when the slope changes from being negative to positive. So now we're going to use the graph of f of x to sketch f prime of x. So here's our graph. Now, some key things to point out. It is at this point here, that's where it goes from being a negative to a positive slope. So it's somewhere around here, around 2. So that means our derivative, I'm going to go with red for this, is coming up from being negative to positive here. It's going to cross here. And then this is kind of hard to see, but if you think about it, this has gone to a positive slope around here, anyway, positive, 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 and then at some point it starts changing, just getting smaller again. That's what we call an inflection point. So I can kind of see an inflection point. I kind of interpret it to be right there. So at this point is where it peaks on the biggest the slope's going to be, and it starts going down again. Now it's a positive slope, and it gets to this point, looks like it's at 3, where it's going to start going down again. So it becomes more negative. So our derivative would be coming up. Oh, I don't know why. Oh, that's my screen has that bad spot in it. So let me clear that off. Okay, we know here, and this was positive, and I'd probably say it's somewhere. Maybe it's a slope of 2, and then it goes back, crosses there. So it's going to come up, cross there, and go back down again. There's a rough idea of what the derivative function looks like. So it says sketch the graph of f of x equals x squared minus 4. On what interval is the graph of f prime of x above the x-axis? So if we were to graph this, draw an axis system. And I'm okay if you want to use a graphing utility like Desmos or a graphing calculator for this. Just knowing how this factors to being x minus 2 and x plus 2 means, and I know it's a parabola, that this can be a parabola that would open up. It crosses at 2 and negative 2 and bottoms out at negative 4. So it looks something like this. Okay. Now, what we want to know is on what interval is the graph of f prime of x above the x-axis. So the slope of the derivative is going to be above the x-axis. So think about how our slope is changing here. And the slope is negative, negative, negative until x becomes 0. Then it starts becoming positive. So our slope in a case like this would look something like the following. So that from 0 to infinity, or I could do a parenthesis there, f prime of x is positive. Okay. Okay, the graph of the slopes of the red function has which color? So think about our red function. It's really confusing what's going on here, but I'm seeing a couple of key things. I'm seeing that it looks like it's bottoming out here. So it goes from a negative to a positive slope here. So we're looking for something that goes from being negative to positive at this point. It peaks here, it goes from having a positive slope to a negative slope. So it's something that's going to start going down and around here. And what do I see? Looks like the green one is negative and it crosses around the same place that bottoms out, and then it crosses again there. So anything else I should consider? We know we're positive here. Which graph of the slopes of the red function has what? The graph of the slopes of the red function. I'm going to go with green for this one. Okay. Derivatives and continuity next. So let's think about differentiability and continuity. Let f of x be a function and a be in its domain. If f of x is differentiable at a, then it's continuous at a. That's an important thing to realize. There's a proof if you want to go over the proof. So here's an example of absolute value of x, f of x equals absolute value of x. And you see the slope from the one side over here is negative 1, the other side is positive 1. So the point is continuous at all these points, but at 0, 0, because we have a slope of negative 1 to a slope of positive 1, the slope's not the same. So it's continuous, but it's not differentiable at 0 because we have slopes being two different things from different directions. Okay. In this case, we have f of x equals a cube root of x has a vertical tangent at x equals 0. So it's continuous at 0, but it's not differentiable at 0. And if we look at f of x equals x sine of 1 over x, it has a derivative that exhibits the interesting behavior at 0. So we see f prime at 0. We're looking at the behavior of x sine of 1 over x, and what's happening there. And it's looking like the limit as x approaches 0 of sine of 1 over x. And we saw this one early in the course. This has a really interesting graph. if you recall, it does this. It never settles down. So this is also not differentiable at 0. So if a function is not continuous, it's not differentiable. But if it is continuous, it may still not be differentiable. And we saw f of x equals absolute value of x fail to be differentiable at 0 because the slopes are not the same at that point of 0, x being 0. And f of x equals a cube root of x fails to be differentiable because you have a vertical tangent line. And then we saw f of x equals x sine of 1 over x is not going to work either. Because of that function. Okay, so now we have this toy company wants to design a track for a toy car that starts out along a parabolic curve and then converts to a straight line. The function that describes the track is to have the form f of x equals 1/10 x squared plus bx plus c, and then that's for x being less than -10, so this point here. And then for being greater than or equal to -10, it's the linear -1/4 x plus 5/2. So the question is, what would b and c have to be for this to work? And then that'd be continuous. So what we're really after is the slope from each direction has to be the same. So let's look at a couple of things. So if we look at around x equals -10, the limit as x approaches -10 of f of x needs to be our f of -10. That's from both directions. So if we look at the limit as x approaches -10 from the left side of f of x, we get 1/10 times -10 squared minus 10 times b plus c, and that's going to give us 10 minus 10b plus c. Now we have two variables there, so now we've got to work the other side to see where we're going to go with this. If we look at the actual defined value, f of 10, -10, excuse me, that'll be the other part of the function. That's -1/4 times -10 plus 5/2. So -1/4 times -10, that's 5/2, plus the other 5/2 gives us 5. So 10 minus 10b plus c must equal 5, which means solving for one of the variables, I'll solve for c. c must equal 10b minus 5 in order for the function to be differentiable at -10. Our f prime of x equals the limit as x goes to -10 of f of x minus f of -10 over x minus -10. What I'm doing here is trying to find what the slope would be at that particular point, so I can use this version. And that's going to be, excuse me, the limit as x approaches -10 from the left. I think I needed that notation here too, but of f of x. Well, we know what f of x is. F of x minus f of -10 over x plus 10. I think to be technically correct, I'm going to leave this negative off right there. Now we're talking about the specific side. So we have the limit as x approaches -10 from the left of 1/10 times x squared plus bx plus c. But we know what c is. C is our 10b minus 5. So 10b minus 5, let's use that c as a parenthesis, minus our f of negative 10 was 5 over x plus 10. And it might be helpful to see this if we now instead multiply top and bottom by 10 to clear out that fraction there. So we have the limit as x approaches negative 10 from the left of x squared minus 100 plus 10bx plus 100b, all divided by 10 times x plus 10. Now we could factor this numerator. We have the limit as x approaches negative 10 from the left. We'd have x plus 10 times x minus 10 plus 10b all over 10 times x plus 10. And the x plus 10s will divide out. This gives us the limit as x approaches 10 from the left, negative 10 from the left, of x minus 10 plus 10b over 10. Now we can apply the limit to be negative 10 minus 10 plus 10b over 10, which is negative 20 plus 10b over 10, which gives us negative 2 plus b, or b minus 2. Now one more point to this is that from the other side, the limit as x approaches negative 10 from the right side of f of x minus f of negative 10 all over x plus 10 needs to be the limit as x approaches negative 10 from the right side of, well, we found that to be negative, turn the page, check those notes again. Yep, negative 1/4 x plus 5/2 minus 5 over x plus 10. And I'm going to multiply everything by 4 over 4 to clear out that fraction. And this gives us the limit as x approaches negative 10 from the right. Yeah. Of, now doing the math up here, that's 5/2 minus 5 is negative 5/2. So it's really a negative 1/4 x minus 5/2 times 4 is going to give us, I'm going to factor out the negative, and the 4 is gone now. So 4, yeah, that's positive now. 5/2 times 4 is going to be 10. So it would have been, this would have been a negative 1/4 x minus 5/2 times 4 equals that negative x minus 10. Factor out the negative, it's negative of x plus 10 over x plus 10, 4 times x plus 10, And these x plus 10s divide out. That leaves us with the limit as x approaches negative 10 from the right of negative 1/4. So getting close to being done, super close. So to make to be differentiable, the limit as x approaches negative 10 from the left must equal the limit as x approaches negative 10 from the right. So our negative 1/4 must equal b minus 2. So b must equal negative 1/4 plus 2, or 7/4. So c equals 10 times that 7/4 minus 5, or 25 halves. So there you go. That was a lot of fun. Okay, let's try another one. So in this problem, find the values of a and b that make ax plus b f of x equals ax plus b if x is less than 3 and x squared if x is greater than 3. Both continuous and differentiable at that change point, which is 3. So this one, after seeing the last one, you think, oh my gosh, this is the worst problem in the world, but it doesn't have to be. So we're looking for the limit as x approaches 3 from the left side of our ax plus b minus, what is our f of 3? That's going to be 3 squared, which is 9. Okay, so minus 9 over x minus 3. And the limit as x approaches 3 from the right side is going to be of an x squared minus 9 over x minus 3, which is the limit as x approaches 3 from the right side of x minus 3 times x plus 3 over x minus 3. And I think we see that the x minus 3's will divide out, and that's going to give us the limit as x approaches 3 from the right side of just x minus 3. Nope, I crossed the wrong things out. Oopsies. So I can get rid of that red. Nope, got rid of the whole thing. Plus x plus 3. The x minus 3's divided out. And that allowed us to have an x plus 3 down here. So that's 3 plus 3, which is 6. Now we use that for the other part. We know these limits have to be the same. And that limit looks like ax plus b minus 9 over x minus 3 needs to equal 6. So that ax plus b minus 9 must equal 6 times x minus 3. Ax plus b minus 9 equals 6x minus 18. And if I add the 9 to both sides, I have ax plus b equals 6x minus 9. We only have a couple choices now. We have one x term on each side, and the coefficients must then be the same. And we have a constant on each side. Those must be the same. So we can conclude that a must equal 6 and b must equal negative 9. And that's it. So not nearly as bad as the previous one. Okay. Well, I hope that helps.